Hello student, hi, I am Vipin Mishra and I welcome you all on the IMS GATE Academy. I hope you all are preparing well for the GATE exam. As the GATE exam is inching closer and closer day by day, now you must be wondering what all are the important topics that you must cover and what type of question you should exactly prepare in order to give a boost to your score. Well, if you are really wondering with these questions, then you are at the right platform right now. Subscribe our channel because we are now conducting a GATE Score Boost series in which we are covering all these aspects and we are answering all your questions regarding to the GATE Booster series. Now go to our playlist and see we have already covered digital electronics, networks, measurement, electrical machine and control system. And today and tomorrow I will be discussing a very important topic, that is very important subject, that is power electronics. When it comes to subjects like power electronics, I have seen students are wondering, sir, how can we remember so many formulas and how to practice these waveforms? Well, I used to say them that they don't really have to remember so much formulas because they are very much approachable. So today we will solve a few questions together and I will tell you how can you make those formulas approachable without even bothering to remember them. Okay. Hi Nikhil, hi Naru, very good evening to you all. So it is going to be a very fascinating session today because we are going to discuss some very important and very fabulous question, fantastic question I have to say. So if you really attend this session, you are going to be benefited at the most. Okay. Yeah. So when it comes to the subject like power electronics, we normally have 4 chapters in it. These 4 chapters are power semiconductor devices, DC to DC converters, rectifiers and inverters. So today I will be covering power semiconductor devices and DC to DC converter, and tomorrow I will cover inverters and rectifiers. So let's get started with the very first topic, which is related to the power semiconductor devices. So if I talk about the weightage of this particular chapter, so normally you will see a question of 1 to 2 marks from this particular topic. Good evening Jagdish. And what are the important topics from where you can expect a question from this particular chapter are: the very first important topic is the power semiconductor devices. You can get a question related to various power semiconductor devices. The next topic is switch realization and switching power loss. You may be asked a question where you have to realize a particular combination of switch, or you have to calculate the switching power losses of a device. And the third important topic is the commutation circuit. So let's get started with the very first question. Now read this particular question with me guys and try to answer it. What has been asked in this question is, which of the following switch will have VI characteristic as shown in the figure below? So we have been given a VI characteristic, as you can see in this figure. Whatever is the switch, it is blocking positive voltage and it is conducting current in both directional. So it is a unipolar and bidirectional type of switch. Now we have to choose among these following options which can have a characteristic similar to what has been given to us. So these are the 4 combination and we have to choose among these. Okay. Now before actually getting into this question belongs to the topic switch realization. Now when you are about to realize a switch, you have to remember one important fact. When you are realizing a switch, the one thing that you have to remember is a switch may be realized based upon the voltage that it will block during its off state. Mind it, the voltage that it blocks during its off state and the current that it will conduct during its on state. So these are the 2 important facts that you should remember. The voltage blocked during off state. The voltage blocked during off state and the current carried by the switch during its on state. These two are the facts that you should take care of. Now, there are two kinds of switches in power semiconductor devices. They can be categorized in two categories. One category belong to the passive switches and one category belong to the active switches. Hi Rupesh, very good evening. So when we talk about the active switch or passive switch, so a passive switch, if we are talking about passive switch, so their conducting state is determined by the voltage applied to them and the current carried by them. Okay, these are the passive switch. They do not have any control terminal. They do not have any control terminal. So their conducting stage, or we can say they may be realized based upon the fact the voltage applied across them. Okay, for example, one passive switch may be a diode. If you see this particular diode, we have applied this voltage and this current. So there is no control terminal in diode. So you can see here, when we apply positive voltage across this diode, it will conduct and it will carry a positive current. But when we will apply negative voltage across this diode, this will not conduct. So it will be blocking the negative voltage. So this is how we will realize this particular passive switch, which is diode. So you can see they do not have any control terminal. But when it comes to an active switch, they normally have a control terminal. An active switch normally has a control terminal, and whether the switch is conducting or it is blocking, that depends upon the control signal given to the particular switch. These switches are called as the active switches. For example, if I talk about an IGBT, BJT or MOSFET, SCR, TRIAC, GTO, all these are the active switches because normally they have a control terminal, and whether they are conducting or they are blocking, that depends upon the control signal given to them. So for example, if I talk about an BJT, so this is a BJT that I have. If this is the applied voltage and it will carry a current in this direction, collector, emitter and base are the three terminals. So now if in order to realize this switch, what will happen? If suppose we have applied this particular voltage V, then whether the BJT will be conducting, that depends upon whether the base signal has been applied across it or not. Suppose if I have applied this particular voltage, and when you apply base voltage and base current, then the switch will be conducting and it will be carrying a current in this particular direction, which is positive current. When you remove the base signal, it will be blocking this particular applied voltage. Means when you remove the base signal, it will be blocking the positive voltage. So you can see this is a passive switch because it has, this is an active switch, sorry, because it has a control terminal. And whether this switch is conducting or not conducting, that depends upon the control signal, isn't it? So this is how you can see this switch is blocking positive voltage when base signal is not given to it, and when you apply base signal, this will be conducting and it will be carrying a positive current as well. So this is how we will realize a active switch or BJT, you can say, isn't it? Similar characteristic you will have in case of, this is BJT that we have. The similar characteristic you will have in case of IGBT as well. So this is an IGBT, and in order to realize an IGBT, the same kind of characteristic it will have, or we can say the same kind of switch realization we will have in case of an IGBT. It will also block positive voltage and it will conduct positive current as well. Now, the third switch that I am going to talk about is MOSFET. MOSFET is also a passive switch, sorry, an active switch. But what happens in case of a MOSFET, you might say this is drain, this is source and this is gate terminal. So if this is the applied positive voltage and it is carrying this particular current, so like the way we have realized IGBT and BJT, similar kind of switch realization we should have. ब्लॉक का मतलब क्या होता है? ब्लॉक मीन्स व्हेन यू आर अप्लाइंग अ वोल्टेज वेदर द स्विच इज इन ऑफ स्टेट. ओके, ब्लॉक मीन्स द स्विच इज इन ऑफ स्टेट. ओके, and conduction means the switch is in on state. I gained a lot of confidence in subject because of your lecture. Thank you so much, Nikhil. So is that clear, Rupesh? Block means the switch is in off state. So when the switch is in off state, which type of voltage it is blocking? Okay, yeah. Now when it comes to MOSFET, okay, when it comes to MOSFET, what will happen? When it comes to MOSFET, ideally the characteristics should be like BJT and IGBT, but due to the internal body diode present here, guys, this will be able to carry current in the negative direction as well. So a MOSFET is a unipolar bidirectional switch. Only this particular fact you have to remember. Rest all the transistor family devices like IGBT, BJT, they are having the same switch realization. They are unipolar, unidirectional devices. But when it comes to MOSFET, due to this internal body diode, it is able to carry current in negative directional as well. Okay. Now come back to our problem. Now when we come back to our problem, see what has been given to us. The switch is carrying current in both direction and it is blocking positive voltage only. What about reverse voltage in case of BJT, sir? Sai, why do you apply reverse voltage across BJT? If you want the conduction of BJT, you will apply a positive voltage across collector and emitter, isn't it? And then when you will apply base voltage, it will either come to on state, and if you remove the base voltage, it will come into off state, isn't it? So this is what is given to us. Now we have to realize which as per the voltage polarity given to us. Okay. Now tell me, now this particular characteristic which is given to us, the switch is carrying current in both the direction. So we have realized MOSFET is carrying current in both the direction. MOSFET is carrying current in both the direction. When it comes to IGBT, it is having this particular characteristic. It is carrying current in one direction only. When it comes to BJT, it is also having similar characteristic. This is V, this is I. It is also carrying current in only one direction. So out of these options, Naru Gopal, both A and B. So we have seen B. Now we have to look forward towards A and then we will answer. Okay, Narul? Good evening, Atul. So guys, from here you can see the D option cannot be correct. C option cannot be correct. B option is the correct option, but we haven't seen about A. Now what we are having in A? Option A, you can see we are having two switches connected in parallel. So what happens when we get two switches connected in series or in parallel? So let me tell you about this particular fact. So when we have two switches connected in parallel, like we have here, we have BJT. This is our BJT, and we have diode connected in parallel to it. So what are their individual characteristics, individual switch realization? So if we talk about BJT, we have realized BJT in this particular manner. This is the applied voltage. This is the given applied voltage that we have. Conduction loss का numerical नहीं हो पाता. Just wait, Rupesh. I have a question related to that as well, and together we will solve and together we will rectify this particular thing right now in this particular lecture. Okay, just now focus on this particular thing because this is one of the most important topic regularly coming into the GATE exam. Okay, thank you, Sandeep sir. So see, when we talk about BJT, you can see we have this particular switch realization and we have a diode connected in this particular manner here. So what about this particular diode, guys? for this particular diode, what will happen if this is V and this is I? This will be able to block positive voltage and this will carry current in negative direction, isn't it? Because this is an inverted diode. We have talked about diode when we have taken this particular combination, isn't it? For this, the switch is realized in this particular manner where it has blocked positive voltage and negative voltage and carried positive current. When it is inverted, just reverse will happen. It will block positive voltage and carry negative current. Okay. So now we have two switches, this one and this one. They are connected in parallel. Now tell me about one fact, guys. When two things are connected in parallel in electrical terminology, what will happen? When two things are connected in parallel, the voltage is same, but they carry different current, isn't it? The voltage is same, means the voltage is common, but they carry different current. So can you see here from this figure and this figure, we have to keep the voltage same and we have to keep the current different, means whatever current are there, we have to take both and we have to take common voltage. So if you see in this figure and in this figure, we have one common voltage, that voltage is positive, but the current that we have in one switch, we are having positive current, and in one switch we are having negative current, and we have to take both the current. So what will be the common characteristic for this particular switch? The common characteristic for this particular switch will be, if this is V and this is I, it will block positive voltage and it will carry current in both the direction, isn't it? So what will happen? This will block positive voltage and this will carry current in both the direction, isn't it? Because two switches are connected in parallel. So what we consider in electrical terminology, the same thing we have to take here as well. Okay. When things are connected in parallel, the voltage is common, current in different. When things will be connected in series, the voltage will be different, but the current has to remain the same. This important fact you have to remember, and the rest will be done. So guys, now coming back to this problem, option A will also be the correct option. So wherever you required a bidirectional current carrying capacity, you can use either MOSFET or a combination of BJT with this diode. Is that clear, guys? Are you getting this fact? Yes. So this is how we will approach towards these problem. Now, I have a very exciting problem for you, and you can expect this type of question in the upcoming GATE exam as well. Now see this particular question. What is given to us? An electronic switch as is shown in figure. So we have an electronic switch in which we have this BJT and diode. They are connected in series, and across this combination we are having a diode connected in parallel as well. Now we have to determine how this particular switch will be realized, and the options are given to us. So now, can you try this? I will give you 1 minute. Okay. Let me check whether you are able to solve this or not. So I will give you 1 minute. Let me be aside. Naru Gopal, option D is correct. Well done, Naru. You are in a great touch of this particular topic. Very well. Very good. So let me see whether everybody can answer this question or not. Whatever approach I have told you, you have to apply the same here. Let me be aside so that you can see all the options. So only Naru has answered this correctly. Yes, Naru, option D will be the correct option. How? Let me tell this to everyone. So guys, we have BJT and diode connected in series first of all. So what we have BJT and diode. They are connected in series, and then we have a diode connected across this parallel combination, this series combination. Okay. Now, when it comes to BJT, which type of characteristic, which switch realization it has? If it comes to BJT, it will block positive voltage and it will carry positive current. When it comes to a diode which is connected in this particular fashion, what will happen? It will block negative voltage and carry positive current. Now these two are connected in series. So what will be their common switch realization? When things are connected in series, the voltage will be different, but the current will be same. So we have to take common current but different voltage. So if you see here, the different voltages are positive and negative. Both types of voltages are there. So we will take both the voltages. So this and this voltage will come here, but the current has to be common, and we have only one type of current here, which is positive. So this is a switch realization for this particular series combination. Now this problem can be asked individually as well, but I have taken somewhat more than that. Now we have a diode connected across this parallel combination as well. So guys, what will be the switch realization for this kind of diode? For this kind of diode, what will be the switch realization? It will be able to block positive voltage and it will be able to carry negative current, isn't it? Now see here, this is figure A and this is figure B. Now what we have this particular series combination and this diode connected in parallel. As you can see in this problem, we have BJT and diode connected in series, and then we have this particular diode connected in parallel. So what will be the switch realization? We have to take the parallel counterpart of A and B. So in parallel, what happens? In parallel, the voltage is common, but the current is different. So we have to take common voltage, but we have to take both the current. So what will be the resultant? What will be the answer, guys? What will be the answer? We have to take common voltage. So when it comes to common voltage from A and B, A is having both kind of voltage, but B is having only positive voltage. So we will take only positive voltage because we have to take common of the voltage. But current we can choose both. So here we have negative current, here we have positive current. So we will take both the current. So this will be the switch realization for the given combination, isn't it? Bidirectional and unipolar. Now see which of the options are having the same answer. Option D. So Naru has answered it correctly. Well done, Naru. Very well done. Okay. Now after that, now see this particular problem. For the composite switch, below identify the correct IV plot. Now see, this is the combination of composite switch given to us. 4 diodes and 1 BJT are connected in a bridge manner. You have to comment how this particular combination can be realized by looking into the option A, B, C and D. Okay, so your time starts now. So let me give you 1 minute because 1 minute is sufficient to solve this problem. And your time starts now. So see it and tell me which can be the correct answer. Naru has again answered this. Naru said it is B, D option which is correct. So let's see what will happen. So as per Naru, it is a 4-quadrant switch. Isn't it, Naru? It is a 4-quadrant switch. So let us see. Let's wait and see what others have to say. Arjun Mane. Arjun is saying it is B which is correct. So as per Arjun, what will be the correct option? B is the correct option. Okay. Think about it more. Okay. And then I will tell you how this particular combination will be realized. Last 10 seconds. Like track. Rupesh D. Very good. So Rupesh and Naru, you are correct. Guys, if you see this particular combination of switch, there are 2 possible ways. You can go from here A to B in this particular manner, This is the first possible way how you can go from A to B. So if you are really going from this particular way, you will get this particular combination. We have one diode and we have transistor, and then we have another diode, and all these are connected in series. This is D1 that we have, and this is D4 that we have. So D1 and D4, and this is our transistor. So one possible way of reaching out B from A is this one. Now can you tell me how will you realize this particular? See, we have already done transistor with a diode connected in series. You have already realized this switch in the previous case. Let me just show you once again. So when we have BJT connected with diode, this is realized in this particular manner. It will block both the voltage but carry current in only one direction. So it will be realized in this particular manner. If this is voltage, this is current, it will block both the voltage but it will carry current in one direction. So this will be the switch realization for this combination. Now if you see, the second possible way of reaching out A to B is, second possible way of reaching out A to B is like this. We can also go from A to B in this particular manner. So if we are making this approach, what will happen? We have this particular combination. We have this combination where D2 and D3 diodes are there. Now if you look into both of them, if you look figure A and figure B, isn't figure B is the inverted case of figure A? See guys, figure B is the inverted case of figure A. So whatever we have obtained from figure A, the inverse will be there in figure B. So if we talk about figure B, how you will realize figure B? So in figure B, we will get just the inverse of figure A. So in figure A, we have both the voltages, reverse will also be the same. But in figure A, realization of figure A, we are carrying positive current. So here we will carry negative current. Okay. Here we will carry negative current. So if this is figure 1 and if this is figure 2, now you can see both these combinations are connected in parallel. So when the things are in parallel, what will happen? You will take both the currents and you will take common voltage. Okay. So if you are taking both the currents and common voltage, what will be the switch realization? If you take both the voltage and both the currents, guys, it will be a 4-quadrant switch. So what will be the answer? Correct answer is option D. So Rupesh and Naru, they have answered it correctly. Arjun, is it clear to you as well? Is it clear to you as well? Did you get the fact how we are realizing a particular semiconductor switch? Very good, very good. So this is all about switch realization, guys. Just remember these facts only and you will be able to solve n number of problems related to a switch, related to the switches. Okay. They may either be connected in series, they may either be connected in parallel, or individual switch combination may be asked. So if you are able to remember these facts, you can solve any problem. Okay. Now see this particular problem. This is a very interesting one, and these type of questions are recently being asked in the GATE exam a couple of time. Okay. So see this particular problem. The correct sequence of given devices in the decreasing order of their speed of operation. In the decreasing order of their speed of operation. Okay. So I am giving you 1 minute for this particular problem as well. So first I just want you to think about it and then together we will answer. Okay. We have to tell regarding the decreasing order of their speed of operation, means the fastest switch to the lowest fastest switch. Okay. Or we can say the slowest switch. So fastest to slowest we have to go. Now tell me which option is correct. I think Naru has answered and she's saying that D is correct option. What about others, guys? Naru 150 10.1 kilohertz. Very good, very good. So see guys, we have to comment. First of all, let me tell that the D is the correct answer. MOSFET is the fastest switch that we have, okay? And after MOSFET, we have IGBT, then power BJT, and at the end we have SCR. Why this is so? Why this is so? Because this is determined by their switching frequency, okay? So if you see the switching frequency of a switch, the switching frequency, which is F, is 1 by T. And do you know this T? T has the on time plus off time of the switch, okay? The T is the time period that the switching time period, so it constitutes T on plus T off time. The time with the switch is taking during its on state, being from coming from off to on state, or the time it is taking from coming from on to off state is the T off time. Now the T off time is having basically TRR, the reverse recovery time, okay? Now there are two kinds of semiconductor devices. One is the minority carrier device and one is the majority carrier device. Minority carrier devices and the majority carrier devices. So guys, devices like if apart from the MOSFET and the Schottky diode, apart from MOSFET and Schottky diode, rest all the devices that we study in power electronics are minority device like BJT, like diode, IGBT, SCR, GTO, all these are minority carrier devices because both electrons and holes participates in the conduction, but here only electrons are participating in the conduction. So if electron and holes both are participating in the conduction, the reverse recovery time means when the device comes from on to off state will be more. But when it comes to majority carrier device where only one type of charge carriers are participating, we normally have low reverse recovery time. So what will happen here? TRR is more, but here TRR, that is reverse recovery time, is very less. So what will happen? Ultimately the T will be more here and the F will be less here, and what will happen here? The T will be less here and the F will be more here. So what will happen? What will happen? Which device can have highest frequency? Which device can have highest frequency? It is the MOSFET which is having the highest frequency. After that it is IGBT, and then we have power BJT, and in case of an SCR we have the lowest frequency, isn't it? Isn't it? So if a device is a majority carrier device, normally there will be less TRR across it, and if we have less TRR, that is less recovery time, then what will happen? Ultimately the T will be less and F will be more, and the operation of device is also a little bit faster as compared to the other ones. So if you can just remember this fact, you can expect a question in the upcoming GATE exam from any of these facts that I have revealed right now. I hope this is clear to you. Yeah. So now moving towards the next problem. So Rupesh, here comes the problem in which you were interested. The problem related to the switching losses, isn't it? So just see this problem. This is a very important concept. Regularly there are questions in the GATE exam from these particular topics, okay? So what has been given to this particular question is, for a power transistor supplying a resistive load, the voltage and current variation during turn on and off are shown in figure. The mean switching power loss at the frequency of 10 kilohertz in watt will be. So how the voltage and current are varying across the device during the on state and during the off state, that are shown to us. Okay, so this is the time that I am asking about. When the device is getting into from off state to on state, this is the time it is taking. When the device is coming from on state to off state, this is the time it is taking. And you can see the total frequency is also given to us, which is 10 kilohertz, isn't it? So guys, on time and off time, they constitute the total time, and the switching frequency is the inverse of total time. So if these times will be more, the switching frequency will be less. Okay. Now, coming to this particular problem, we have to calculate the power loss across the switch. We have to calculate the power loss. So how do you calculate the power loss? In order to calculate the power loss, guys, first of all, you have to calculate the energy loss. And energy loss you can calculate for the time period, whatever is the voltage and current, that is the multiplication of voltage and current, which is the instantaneous power, and when you will differentiate it, you will get the energy loss. Okay. Now if you see this particular problem, if we are writing the expression for voltage and current and then we are multiplying them, and after that when we will be integrating it, it will become a more complex and more calculation will be involved here. So guys, we have a trick here. If you see that voltage and current both are varying here, similarly the voltage and current both are varying here, the E loss you can calculate by using this particular formula. So energy lost during on state, this will be equals to VCC ICS upon 6 into T on. What is VCC? This voltage is VCC and this current is ICS. Similarly, this current is ICS here and this voltage is VCC here. Similarly, we can calculate E during off, energy loss during off, by using the same formula, VCC ICC by 6 into T off. Okay. So by using these two formula, you can directly calculate the energy losses. Now put the values and see what will be the answer. VCC here is 300, ICS here is 150 divided by 6, and what is T on? T on is 2 microseconds. So when you will calculate it, this will come out to be 15 millijoule. Again put the values here. VCC is 300 and ICS is 150 divided by 6 into T off is 4 microseconds here. So when you will calculate it, this will come out to be 30 megajoule. Now what will be the total E? E total will be E during on plus E during off. So when you will add them up, you will get the total energy loss to be 45 megajoules. So this is how you can calculate both the losses. How to find conduction loss is PWI model. I didn't get your question, Rupesh. When you are about to calculate the conduction loss, you can expect this particular problem, or I have one more problem for you which you can expect in the GATE exam. Okay. Apart from that, you don't have to invest your time or you don't have to be confused about the things. Okay. So just focus on this particular thing. Either you may get this kind of problem where you can use direct formula of calculation of E loss during on and off period. So this is how you will calculate the total E. Now when it comes to the power loss, it will be E upon T, or you can say E into F. So E we have 45 millijoule, and what is the frequency? The frequency given to us is 10 kilohertz. So when you will put 10 kilohertz, I think it will be 450 watts, and that will be the correct answer. Is that clear? Piecewise linear model. Rupesh, you can expect those kind of questions in analog. Okay, that kind of question will not be there in power electronics. I'm getting what you are talking about. You can expect those kind of questions in analog. Okay. So we are having analog session scheduled as well in upcoming days. So there you can expect that particular question as well. Okay. Right now here in power electronics, either you will get this kind of question, okay, and a next kind of question that we have that you can expect in the exam as well. So is that clear? When voltage and current both are varying in this particular manner, you can use this particular formula directly in order to calculate E on and E off. Okay, then total E will be calculated, and when you will divide E by T, you will get the power loss. Is that clear? So this is the one kind of problem that you can expect. But what happens if the voltage and current both are not varying, like you can see in this particular problem? Okay, see, just read this problem with me. The voltage across and current through the MOSFET. So which option will be correct here? Option C will be correct. Okay, I think Naru has answered this correctly. Very good, Naru. I think you are very well prepared for the exam. Very good. Now just see this particular question. The voltage across and current through the MOSFET during turn-on transitions are shown below. So how the voltage and currents are varying across the MOSFET during the turn-on transition, these are given to you. Now what we have to calculate, the switching frequency is given 100 kilohertz, and we have to calculate the power loss in the MOSFET. Okay, we have to calculate the power loss in the MOSFET. Now you can see both voltage and current are not varying at the same time, as we have in the last case. If you see, during this particular time both the voltage and currents are varying. During this particular time both the voltage and currents are varying, but here what we can see, both voltage and currents are not varying at a time. Here the voltage is constant for this duration, current is increasing, but here what happens, the voltage is decreasing but the current is constant. So if you see this particular problem, how to approach for it? So guys, I have told you, in order to calculate the E, what you have to do, you have to integrate the voltage and current. First you have to multiply them, and then you have to integrate for that particular duration. Means what is this? This is instantaneous power, and when you will integrate it, you will get the E. So if we apply this particular trick here, so for let me call T1 to be 10 microseconds, and let me call T2 this to be 20 microseconds. So first of all, for T1, that is 10 microseconds, what do we have? We have voltage which is constant 50, and we have current, or we can do it otherwise as well. See here, since for the T1 duration the voltage is common, so take it out, and the current is varying, so let it be here. For the next time, that is T2, if you see, the current is common, so take the current out and let the voltage be there because it is varying. So like the way you can do here. Now what is this? This represents the area of the current curve, and what is this? This represents the area under the voltage curve. So what will be the area under the voltage and current curve, guys? What is VT here? VT is 50 here, and this is nothing but the area under the current curve. Yes, Rupesh, you are correct, but that belongs to the analog subject. Different concepts are involved there. So analog, it will come in analog subject. So when analog will be covered here, definitely you will get that question here as well. Okay, Rupesh? Here we are discussing power semiconductor devices in power electronics. So I have not taken a question regarding that because this is not the case here. This is not important for power electronic subjects. Okay. From here you can expect that kind of problem. Is that clear, Upesh? So focus on these. What it represents? It represents the area under the current curve. So now you have to calculate the area under the current curve. So it is a triangle. So you can calculate it. 1 by 2 into 10 into 10 microseconds means 10 into 10 to the power minus 6 plus, when it comes to the second curve, I is common and that is 10, and this represents the area under the voltage curve. So how do you calculate the area under the voltage curve? Again, it is a triangle. So how do you calculate it? 50 into 20 microseconds. Okay. Now solve it, guys, and tell me what is going to be the answer. Naru has already solved it, and Naru is saying 7.5 millijoule or megajoule. 7.5 millijoule or megajoule. What answer I am having is 7500 into 10 to the power minus 6 joule. 7500 into 10 to the power minus 6 joule. Okay. But we have to calculate not about the energy, it's about the power losses, and the frequency is 100 kilohertz. So the frequency given to us is 100 kilohertz, and the power loss we have to calculate. So the power loss is E by T or E into F. So what E we have? We have 7500 into 10 to the power minus 6, and the F value that we have is 100 into 10 to the power 3. So I think 750 watt, that will be the answer. Are you getting the same answer, Naru and Rupesh? Nikhil, Subodh, are you getting the same answer? 750 watts. Very good, Naru. Well done. So Rupesh, are your doubts are clear? Are you getting these facts? What am I telling you? In power electronics, from this particular topic, switching loss, you can expect a problem like this. Okay. Piecewise model and everything else, that you have to focus when it comes to analog subject. Okay. That deep question will not be asked here in power electronics. Just focus on these topics and you will get a similar questions in the upcoming exam as well. So is that clear, guys? Do you have any doubt? And are you enjoying this gate booster series as well? Just give me a reply. Very good. So I hope these concepts are very clear to you. Now it's coming to the commutation circuits. Very good. Commutation circuits. So see what has been asked in this particular question. It is given that the current commutation circuit is shown to us. This is the current commutation circuit that we have. If the capacitor and inductor has the value of 20 microfarad and 7.5 microhenry respectively. So we have the value of capacitor and the value of inductor given to us. The voltage across the capacitor for which the SCR gets turned off. We have to determine the voltage across the SCR applied when it is getting off. Means the reverse voltage that the capacitor will apply, we have to determine that particular voltage here, guys. So see, you know that the capacitor voltage is given by capacitor voltage is VC, and it is given by Vs cos omega t. The capacitor voltage is Vc and it is Vs cos omega t. That is the capacitor voltage. Now, initially the capacitor is having this polarity. This is the polarity that the capacitor is having, and it is having a current flowing across it, which is known as IC. And this IC current is what? This IC current is IP sin omega t, or we can say Vs under root C by L sin omega t. So these two things are very well known to us, the capacitor voltage and the IC current. Now when the capacitor is having this polarity initially, the diode will normally be off, isn't it? But it is following the cos curve, so when it will change its polarity like this, so what will happen? Initially the capacitor voltage is appearing as a forward bias to this particular thyristor. When it will change its polarity, that particular voltage will act as a reverse bias for this thyristor, isn't it? When the capacitor will change its polarity, what will happen? The TA thyristor, it will be off due to this capacitor polarity, and now the diode will be conducting. So when the diode will be conducting, it will be carrying a current IC, and here we have the current ITM, isn't it, guys? So now when you will apply KCL, what you will get? ITM plus IC, they both add up and they will constitute a current I naught. Are you getting this fact? Both these will constitute the current I naught. Now what will be ITM from here? ITM from here will be I naught minus IC. Okay. Now let at an instant T2, let an instant T2 where what happens? I naught equals to IC. So when I naught will become equals to IC, guys, what will happen? ITM will be equal to 0 and thyristor TM will be off. And you can see here capacitor is applying the reverse voltage across it, isn't it? The capacitor is applying a reverse voltage across it. So this is the instant. At the instant T2, I naught will equals to IC and then ITM will be equals to 0, and that is the moment where you will get the thyristor TM getting off. Now what will be that instant? During that instant, guys, what you have? You have I naught getting equal to IC. So what is IC? IC is Vs under root, or let me write this IP only. So what is IC? IC is IP sine omega naught, and the instant is T2. This is equals to I naught. So what will be omega naught T2? Omega naught T2 will be sine inverse I naught upon IP. Now I naught is given to you. What is I naught? I naught is 140, isn't it? And when you will calculate the current IC, what will be the current IP? The current IP, if you calculate by using the formula Vs under root C by L, you can calculate it. So omega naught T2 we have opted. So this is the omega naught T2 instant where the capacitor is applying a negative voltage across the thyristor and it is getting off, that we have determined. Is that clear? Now capacitor is applying a reverse voltage during that moment. How is the capacitor voltage is given by Vc equals to Vs cos omega naught T. So when this is happening, actually whatever is the capacitor voltage, that is acting as a reverse voltage, and that voltage will be at the instant omega T2. So from here, instead of omega T, we will put omega T2 here. So ultimately what will happen? You will put here, what is omega T2, guys? It is sine inverse I naught over IP. So what you have to do right now, all you have to do is to put the values and get the answer. So what will be the value of IP if you put here? IP you can calculate what is Vs. It is 220 and under root C by L. So both the C and L are given to us. C is having a value 20 microfarad and L is having a value 7.5. So 20 upon 7.5, because both are in microfarad, so that will be cancelled. So I am not writing that, and you will get 358.6 ampere here. Now put the values here. Vs is 220 volt. This is cos sine inverse I naught is 140. IP you have calculated is 358.6. So once you will solve this, you will get an answer 202.5 volt, isn't it? So guys, when it comes to the commutation circuit, I have seen students really struggling to remember the formulas and waveform. Now you can see how beautifully we have approached the required formula without even bothering to remember it, isn't it? Naru, Nikhil, Subodh, Rupesh, are you getting this fact? How easily we have approached for this formula without even bothering to remember so many formulas and so many waveforms. Are you getting this fact? So this is the beauty of power electronics. You can derive any of the formula. You can make your approach towards any of the formula very easily and in a very precise manner. So you don't have to worry about the things कि we have so many formulas to remember. Are you getting this fact? So see, by just looking into the circuit, and they always give you the circuit, you don't have to remember the circuit as well, And this is how you can make your way approach towards this particular formula required to solve this question. So I hope this is very, very clear to you. Very good, Naru. Okay. Now, in the continuation, let me have another problem. Now see this problem. The last problem was related to the current commutation circuit. Now this problem is related to the voltage commutation circuit. So a voltage commutated chopper operating at 1 kilohertz, the frequency is given to us, is used to control the speed of a DC motor, as we can show here. As we can see here, a DC, we are controlling the speed of this particular motor here, and the voltage commutation chopper is used to turn off the thyristor. The load current is assumed to be constant at 10 ampere. Guys, the load current is 10 ampere. I naught is given to us, which is 10 ampere. The peak current through the thyristor Tm is. So what will be the peak current across the thyristor Tm? That we have to determine, that we have to calculate here. So again, see how very easily we can approach towards the whatever the formula is required. Now we don't have anything in our mind. We don't have to remember any formula. Now see how beautifully we will derive the particular formula required. Okay, see what will happen. This is the capacitor. So initially its polarity will be like this. So due to this polarity of capacitor, Ta will be off and this diode will be conducting. So there will be one current flowing in this particular circuit in this manner, and that current is IC. So we have one current flowing here, which is IC, and one current is flowing across this main thyristor as well. So when we will apply KCL here, what do you will get? What do we get? ITM, this is equals to what? This is equals to IC plus I naught. Yes or no, guys? See, simple logic. The ITM current by applying KCL will be IC plus I naught. Okay. Now you know what is IC. Whenever we have an LC combination, the current is IC equals to IP sin omega t. So when it comes to the peak value of thyristor current, we have to take the peak value of IC, and this will be the current. Now what is IP? IP is calculated by the formula Vs under root C by L plus I naught. Now everything is given to us, guys. Just put the formula and get the value. What is Vs? Vs is 300 volt. What is C here? C is 1 microfarad. And L is also in micro, so I am not putting 10 to the power minus 6 here. 1 by 50 plus what is I naught? I naught is given to us, which is 10. So once you will solve it, you will get the answer. Once you will solve it, you will get the answer. So what is the answer that is coming here? 52.42. That will be the answer. So again, you can see, before solving this particular question, I haven't talked about the formula required to solve this question, isn't it? What we have done, we have instantly derived the formula required to solve the question, and this is the beauty of power electronics. You don't have to remember so many things, guys, but the facts among the student is that we have to remember a lot of things. That's not the reality about power electronics. Okay, it's a very conceptual subject. If a circuit is in front of you, you can drive, you can calculate n number of things without even bothering to remember anything. Is that clear? So guys, are you really enjoying this session? Because we are solving some beautiful problems, and I'm also telling you how you can make your approach, or how can you reach to a particular formula required to solve the questions. Naru is saying yes, दोनों नए क्वेश्चन थे सर, but solved very easily. Very good, Naru. And that's what I want. That is the purpose of this particular session. That is the purpose of conducting this GATE score booster series. We just want you to be that much perfect so that your score will be boosted. Okay? Yeah. So guys, this is the end of the first chapter, which is power semiconductor device. So you can expect a questions from switch realization. We have covered that topic. You can expect a question from the power losses of device. We have covered that questions. Okay. You can expect a question across all the devices about their reverse recovery time, about minority majority carrier devices, about their reverse recovery time, about their switching frequency, about their frequency of speed of operation. So we have, in one question I have covered all these topics. Okay. After that we have seen the commutation circuit as well. Okay. Now I am coming towards the most important topic or most important chapter, which is DC to DC converter. Rupesh, rectifier and inverter I will cover tomorrow. Okay. Today I am covering power semiconductor devices and DC to DC converter. Tomorrow I will cover rectifier and inverter. Okay. So don't worry, everything will be covered here. You don't have to worry at all. Everything will be covered here. Okay. So now guys, I'm talking about the next chapter, which is the very important chapter, not only as far as the power electronics is concerned, as far as the gate exam is concerned, as far as the score of gate is concerned. This is a very important chapter because I'm very sure, and you can see the pattern of gate exam. Every year there are 4 marks of questions coming from this particular chapter only. I hope you all will agree with me. This is a one chapter across the gate syllabus from where it is very sure that a 4 marks questions, 4 marks, total 4 marks of questions will definitely be there in the exam, isn't it? This is so much important. Okay. Now again, what are the important topics? Different converters, the buck converter, the boost converter and the buck boost converter. These are the 3 important topics that we have. In case of buck converter, the output voltage is less than the input voltage. In case of boost converter, the output voltage is greater than the input voltage. And in case of buck boost converter, we can have both the things. Either we can get the voltage greater or we can get the voltage less than the input voltage. Okay. So these are the important topics as far as this particular chapter is concerned. And mind my words guys, this is a very important chapter. Okay. Now again, there is a myth regarding this chapter that this is full of formulas and it's very difficult to remember. Now see, I will make you learn all the formula at the end of this session, and I will tell you in case you forget any formula, how you can approach for a particular formula very easily. Okay. So let me just read this particular question, first question from this chapter. What has been asked in this question is, a step down chopper fed from a 220 volt DC is operating on a chopping frequency of 1250 Hz and a duty cycle of 0.5. The RMS inductor current will be, guys, this particular thing has never been asked in the gate exam. Be ready. Rest everything they have asked, this particular thing has never been asked in the gate exam. This particular question which I have designed, be ready. This might be a question in this particular year's gate exam. Okay. What we have to calculate here? We have to calculate the RMS inductor current. Okay. What type of chopper it is? It is a buck converter. Okay. So what happens in a buck converter? If I talk about the inductor current and how it varies. So in any of the choppers, whether it is buck converter, boost converter or buck boost converter, what happens with the inductor current? It increases from minimum to maximum value, that decreases to the minimum value, then increases to the maximum value if we are considering the continuous conduction. Okay. If we are considering the continuous conduction, it is increasing from minimum to maximum value and then decreasing to minimum value. If this is my on time, then the inductor will be storing the energy and the inductor current increases. And if this is my off time, then what will happen? the inductor releases energy and the inductor current decreases linearly from maximum to minimum value. So this is how the inductor current varies. And what is the average inductor current in case of buck converter? So if you see the figure, the inductor will carry the load current all the time, isn't it? So if I talk about what will be the average inductor current, this will be equals to I naught. The average value of inductor current is I naught here, and you can calculate I naught very easily by V naught by R. And what is V naught in case of buck converter? V naught is given by dVs, okay, where D is the duty cycle. So see what has been given to us. The duty cycle that we have is 0.5 and Vs value is 220 and the resistance is 10 ohm. So just put the values. It is 0.5 here, this is 220 and the resistance that we have is 10 ohm. So from here you can calculate, the I naught. So what will be the I naught here, guys? Can you just tell me, can you solve this and tell me what will be the I naught current here? This will be 11 amperes, okay. Now we have to calculate the RMS value of it. Now guys, this is known as the del IL, the peak to peak ripple. This is known as the del IL value, the peak to peak ripple. And if this is del IL, this amount that we have, this amount is del IL by 2. Now if we are to calculate the RMS value of this inductor current, so this is a triangular wave and a shifted triangular wave, okay. So what will happen in this case, if we are to calculate the RMS value, this will be equals to the IL average so this will be equals to IL average, or IL average is what here? IL average is basically I naught. So directly we can write here I naught square. This will be equals to I naught square plus del IL by 2 divided by root 3 square, okay. So this is how we will calculate. If this would have been a perfect triangular wave like this, if suppose this would have been a perfect triangular wave like this, where this is its maximum or minimum value like this, so what happens, the RMS value will be what? RMS value will be simply Im by root 3, because here the average value is 0. But it is a shifted wave. So how do you calculate this particular thing? You will calculate this particular thing by using this formula, okay. The shifted amount, here the shifted amount is 0. The average value is 0 here. The shifted amount is 0 here. So we don't put there. And this is what? This is the amount above or below the average value. So what is the amount above or below the average value, guys, here? The average value is I naught. Above it we have del IL by 2. So that will be the IM of this case. So del IL by 2 upon root 3 square plus I naught square, isn't it? If we have different frequency sinusoid, how do we calculate the RMS value? It is equals to under root of V1 square RMS plus V2 square RMS plus V3 square RMS, like that. So similarly we have calculated the RMS value here as well, okay. I hope you are getting this fact. Is it clear to everyone? How do we have calculated this particular value of the inductor RMS current? So this is the formula of calculation of RMS value of inductor current. So you can practice this formula very well, guys, okay. Now if you are to solve this particular expression, I naught value you already have. All you have to get is del IL. Now what is del IL, guys? What is del IL here? Del IL is D 1 minus D Vs over FL. Now if suppose you forget this particular formula, del IL, peak to peak ripple current, if suppose you forget this particular formula, you can derive this very easily. You can derive it. How you can derive it? Let me just tell you. So guys, in the figure, tell me when the switch is on. So what will happen when the switch is on? if this is the inductor voltage, this is the switch voltage, and this is the output voltage, if you apply KVL, when switch is on, when you apply KVL, what will happen? Vs minus VL minus V naught, this is equals to 0, or VL will be equals to Vs minus V naught, isn't it? So what is VL? VL is Vs minus V naught here, okay? VL is Vs minus V naught here. So when the switch is on, the inductor voltage is Vs minus V naught. I told you we just required the circuit and rest the things will be done, and the circuit will always be given to you in the problem. Now what is VL? VL is basically L DIL by dt Vs minus V naught. This is when? This is during T on, and T on might be written as dt as well, okay? Now guys, tell me, what will be the DIL, the change in the inductor current? So the inductor current is changing from maximum to minimum or minimum to maximum value every time. What will be the dt? It is, this change is happening during the T on time. So this will be Vs minus V naught by L. Now what is Imax minus Imin? This is del IL, the peak to peak current. Now this will be equals to Vs minus V naught upon L into dt. Now Vs is Vs. What is V naught? In case of a buck converter, the V naught is dVs upon L. T you may write 1 by F, and one more d is there. Now when you will take common, you will get d1 minus d Vs over Fl, isn't it? The same formula I have used, if you see. So by practice, this formula isn't in my mind, and I have written it directly. But in case you forget it, this is how you can remember it. Now this is the buck converter. If suppose this would have been the boost converter, or if this would have been the buck boost converter, the same process you would have applied and you would have got the expression. If this would have been a boost converter or a buck boost converter, instead of Vs minus V naught, we will have Vs only here. So in case of boost converter or buck boost converter, you will get a formula dVs upon Fl, isn't it? Are you getting, guys? So this is how you can very easily calculate whatever formula is required. Isn't it surprising? You don't have to remember anything. You don't have to remember anything, guys, when it comes to power electronics. So this, see, we have derived this particular formula. Now what will be the value here? The d value given to us is 0.5. 1 minus d is again 1 minus 0.5. Vs is 220 divided by the frequency. The frequency given to us is 1250 and the L value is 15 millihenry. So 1250 into 15 millihenry. Now you have to solve this expression and you have to tell what del IL value you are getting. So you will get 2.93 ampere from here. So see, we have calculated del IL, we have calculated I naught here. Okay, Naru has already calculated the answer. Very good. Now again tell me, what will be the answer? IL RMS. What will be that? We have used the formula I naught square plus del IL by 2 divided by root 3 square. So what will come? This will be I naught is what? I naught is 11 plus del IL is 2.93 divided by 2 divided by root 3 square, and after that you will get an answer 11.03 ampere. So see, which option is having the correct answer? B. Option B is correct, and Naru is getting the same answer. Very good, Naru, Amit, Nikhil, Subodh, Sachin, very good. So guys, you can see how very easily we have approached towards the formula that is required. Okay, and this question that I have fabricated is very, very important. You may expect this particular question in this year exam because this has never been asked. You have never been asked to calculate the RMS value of inductor current. So this shall be a question in this year's paper. Okay, and how to approach the different formula if suppose you have forget, that already we have discussed. I hope you are enjoying this. So this is all about this question. Now see the next question. Now guys, see the next question, the buck converter. This is also related to the buck converter. So a buck converter produces 18 volt from 48 volts. So let me write what has been given to here. 18 volt it is producing, that is V naught is 18 volt from 48 volt, that means the source voltage is 48 volt across 10 ohm resistance. So what is the resistance given to us? The resistance given to us is again 10 ohm. The output voltage ripple must not exceed 0.5%. The output voltage ripple means the ripples in the output voltage is 0.5%. Let's see whether this data is useful or not. So that the converter operates at the boundary of continuous conduction. That's fine. The RMS inductor current is, so again we have to calculate the RMS inductor current. Okay. So what formula is required? I already have discussed. So let me give this particular question. I am giving you 2-minute time and I can expect an answer from your side. So let's see whether you are able to solve this or not. The same kind of questions we have with this particular data given to us, we have to solve this case. Okay. So let me be aside, take your time and calculate the correct option. Take your time guys. More than 1 minute is there and you can solve this problem in 2 minutes. Okay. So 10 seconds are remaining. Hurry up guys, 10 seconds are remaining. And the time is over. So what is the problem in this question guys? Again we have to calculate the same thing, RMS value of inductor current. So what will be the RMS value of inductor current? Again it is a buck converter or whatever converter it is, this thing will remain same here. Okay. I naught square plus I naught value will change. Okay, this is what, this is IL average. So this will change converter to converter. This is buck converter. So this will be the same here. And this is how we will calculate this. So we require I naught and del IL. So how to calculate I naught? I naught in buck converter is V naught by R and V naught is dVs. So this will be dVs by R. But do we have dVs? Guys, we have V naught given directly. So we can put V naught directly. What is R? R is 10. So we will get 1.8 ampere of current. Now calculate the duty ratio as well. So duty ratio will be what? Duty ratio will be V naught over Vs. So how much is V naught here? V naught is 18. V naught here is 18 and Vs is 48. So I think we will get 0.375 of duty ratio here. Yes, exactly. Now we have calculated duty ratio, I naught here. Next thing that we have to calculate is del IL. Now I think you know that how to calculate del IL in case you forget, but I think by practice this will be there in your mind. It is d1 minus d Vs over Fl. Okay. So I think we don't have the L value here. Do we have, guys, L value? L value is not given to us. And one thing is given, that it is operating at the boundary of continuous conduction. So guys, it is operating at the boundary of continuous conduction. So when the converter is operating at the boundary of continuous conduction, what will happen? Its inductor current will be like this. It is operating at the boundary of continuous conduction. Okay. So when it is operating at the boundary of continuous conduction, what will happen? The I minimum current, that will be equals to 0. This is the boundary of continuous and discontinuous conduction. If the I minimum current becomes negative, that means that the converter is operating in the discontinuous mode. But when it is on the boundary, I minimum value will be equal to 0. Okay. Now, how to calculate the I minimum value? If you see, this amount is how much? This amount is del IL by 2. So I minimum will be what? I minimum will be IL average minus del IL by 2. This is equals to 0, isn't it? So when you will put this, what is IL average? IL average is I naught minus del IL by 2. This is equals to 0. You may put it dVs upon R. And what is del IL? Del IL you have d 1 minus d Vs over Fl. So from here, if you solve for L, you will get L equals to 1 minus d R by 2F. This is also the formula for calculating the critical value of inductance. Okay. So we were doing something else and we have obtained something else. So how can you calculate L value? By using this particular formula, you can calculate the L value. This is the formula of calculation of critical value of inductance. And you can see how very easily we have approached for it. So now calculate L first. So what is L? L is 1 minus d R by 2F. All the data is given to us. What is the value of d here? D value is 0.375. What is the value of R? R value is 10. And how much is the frequency? Frequency is given to us frequency value is given to us. I think frequency value is missed here. Take the frequency to be 40 kilohertz here. Okay, take the value of frequency to be 40 kilohertz here. So once you put the value here 40 kilohertz, and the value of R that we have to take is, the value of R is given to us and that is 10. Take the frequency is not given here. So you can take the frequency value to be 40 kilohertz. So after that, the L value that you will get is 78.1 micro Henry. That will be the L value that you will get from here. So once you have calculated L, you will calculate D. So what will be D? What will be D here? So if we put the values in the formula, the D value here will be 0.375, 1 minus 0.375 into Vs. How much is Vs? Vs I think is 48 divided by the F is 40 kilohertz. And the L value we have calculated it 78.1 into 10 to the power minus 6. So from here you can get the del IL, and del IL will be 3.6 ampere. So what will be the del IL by 2, guys? It will be 1.8 amperes. Isn't it? Naru is saying, sir, can we use del IL equals to 2 into IL average? Yes, of course, Naru. You can also use that here as well. Okay. Naru is saying that, sir, can we use IL average equals to del IL by 2? Of course. You can use that formula as well. Okay. When we are considering the conduction to be at the boundary, then what you can see here is IL average is equals to del IL by 2. So of course you can use that also. Okay. There are two possible ways. Whenever you are given with this kind of problem, either you can do I minimum equals to 0 or you have to do IL average equals to del IL by 2. What happens in case of boost converter and buck boost converter? It's not so easy to calculate IL average. So better if you remember this particular formula, because by here you can get it very easily. So it does not matter, you can apply this as well if you have a better practice for that. Okay. So del IL by 2 and the IL value we have calculated. So now it's time to calculate the RMS value of inductor current. So inductor current RMS value will be what? It will be I naught square plus del IL by 2 divided by root 3 square. So I think I naught value is 1.8 square plus del IL by 2 is also 1.8 divided by root 3 square. So finally when you will solve it, what is the answer that you are getting? The answer will be 2.078 or approximately 2.1 ampere. So that will be the answer. Yes, Naru, your answer is again correct. Very good. Very good. Nikhil, Subodh, are you getting the same answer as well? Rupesh, are you getting the same answer? So again you can see whenever you are asked about calculating the RMS value, you can calculate it very easily, isn't it? Only two data are required, the I naught value and the del IL value. So in the first problem, if you see, all the data has been given to calculate IL, del IL, and in the second problem the L is not given to us. So I have shown you how you can approach for calculating the L value. You may get a problem in gate where only this L value might be asked or this resistive value resistance will be asked. So be prepared for that kind of question as well. It has been given to you that the converter is operating at the boundary of continuous and discontinuous conduction, and you have to calculate either the value of R, L or R. Okay. So be ready to apply only this particular, thing, and you can get a different problem out of this particular topic as well. Okay. So be ready for that kind of question as well, guys. So I hope this is understood to you and you are enjoying these questions as well. Now in the continuation, I have another question for you, a very beautiful question, and the question in which most of the students struggle. I have seen them struggling. Let's see what has been given in this. The switch shown in figure is ideal. The switch is ideal. The value of duty ratio so that the converter operates at the boundary of continuous conduction. So it has been given that the converter is operating at the boundary of continuous conduction. At that time, what will be the value of duty ratio? Now, can you tell me what we have to do? What we have to do? This is a buck converter again. So what we have to do? At the boundary of continuous conduction, what happens? At the boundary of continuous and discontinuous conduction, guys, what happens? Two condition we can use. Either you can put I minimum to be equal to 0, or what Naru told us, then we can do also IL average, this is equals to del IL by 2. Both the condition, whichever is suitable to you, you may apply that. Okay. So I minimum is equals to 0. How do you calculate I minimum? I minimum you will calculate when you will subtract del IL by 2 from IL average. This is a common sense that we have to use from looking into the waveform, isn't it? Now what are the different values? When it comes to IL average, what is the value of IL average? IL average is I naught here. What is del IL? D1 minus D Vs over FL. I think you might have remembered this formula because we are using this formula very frequently, isn't it? Now I naught will be dVs upon R minus D 1 minus D Vs over 2 FL. Okay, this is equal to 0. Now tell me, after that what will happen? After that you will get, when you solve it, you will get 1 by R. This is equals to how much? 1 minus D upon 2L 2FL. Okay. Now we have to calculate D here. So what will be D? From here we will get 1 minus D. This is equals to 2LF upon R. Okay. Or D equals to 1 minus 2LF upon R, or we may also write it 1 minus 2L upon RT. So this is a very, very important formula, guys, that we have obtained here. When the converter is operating at the boundary of continuous and discontinuous conduction, you can calculate the value of duty ratio by using this particular formula. Okay, and you don't have to remember it at all, because see, we have derived it very easily. So at any instant you can derive this formula. So don't put pressure on your mind or for remembering this particular formula. So what value of D we have obtained? D is 1 minus 2L by RT, or 2LF upon R. Now see what has been given to us. What formula we have derived? D is equals to, see whether frequency is given, frequency is given. So we have derived D to be equals to 1 minus 2LF upon R, isn't it? 2LF upon R. So put the values here. 1 minus 2 into, what is the value of L? L is 5 millihenry. What is the value of F? 100 kilohertz. And what is the value of R? It is 2.5 kilo ohm. So what you will get when you will solve it, you will get the value of duty ratio to be 0.6 here. Very good. Excellent, Naru. Excellent, excellent. Nikhil, Subodh, Rupesh, Sachin, are you getting the same answer? Very good. Okay. So tell me, guys, by solving, I think we have almost solved 4-5 questions from this particular topic, choppers, DC to DC converter. Do you really want to remember all these expressions, or you have the enough confidence that you can derive these expressions whenever you want? Tell me, guys, are you getting the feel of this topic? Are you getting a feel of this topic? Will you even try to remember these formula, or you can derive these formula wherever and whenever you want? Which approach you will like to prefer? Tell me, guys, which approach you would like to prefer? Which approach you would like to prefer? Yes, very good. So you don't have to remember so many formulas, because you have others 9 to 10 subject as well, which you have to cover in order to get a great score in GATE. Okay, so don't bother to remember the formulas. You can derive them anywhere, anywhere and anytime you want. Okay, now by using this particular principle, let me see, are you able to solve this problem? Are you able to solve this problem? What has been given in this problem is, in the chopper circuit shown in the figure, the input DC voltage has a constant value 220 volt. The switch S is operated with a switching period of 50 milliseconds. Okay, the T on period is given to us. First of all, what is given? Vs is given. Vs is 220 volt, and what has been given? The switching period. Switching period means the total T, guys, not T on. The switching period T is 50 milliseconds, in such a way that the conduction is at the boundary of continuous and discontinuous conduction. Whenever you see this particular statement, write I minimum equal to 0. That has been given to you. Okay, the maximum value of inductor current will be what? That you have to calculate. So you have to calculate the maximum value of inductor current, means what will be the I max. That is what you have to calculate. So let me give you some time for it. because I am sure you can solve this problem very easily. Okay, so I have given you 1 minute. Whatever are the formulas required, we have already covered. So you can solve this problem very easily. Solve and tell me the answer. So I have given you 1 more minute because I know that you can solve it. So Naru has calculated. She is saying B is the correct option. Yeah, absolutely correct, Naru. B is the correct answer. Very good, very good, very good. So see, it is what? It is again the buck converter and it is operating on the boundary of continuous and discontinuous conduction. So from the last problem that we have discussed, guys, we can calculate the value of D. If this is a scenario, we can calculate the value of D. Okay, how we can calculate the value of D? By the experience, we know that we can calculate the value of D by using this particular expression, isn't it? And for this we have been given everything. What is the value of L here? 100 millihenry. And what is the value of T? It is 100 millihenry. And what is the value of T? It is 50 milliseconds. So what will be the D value here? What will be the D value here? Oh, we haven't put the value of R here. Na? R value is also 10. So we have to put one more 10 here. So I think the D value coming out to be 0.6. Whether the D is 0.6? Are you getting the D value to be 0.6, guys? And once you have calculated D, you can calculate del IL, which is D 1 minus D Vs over FL. So what is the D? D is 0.6. 1 minus 0.6. Again, what is the value of Vs? Vs is given to us 220 volt upon what is L? L is 100 millihenry. Okay, 100 millihenry. And T, 1 by F is T. So we can put the value of T, which is 50 milliseconds here. So from here you will get the value of del IL to be equals to what? What will be the value of del IL, guys? 26.4. This will be the del IL, 26.4. Now IL max, you have to calculate the maximum value of inductor current. So that will be equals to IL average plus del IL by 2. Now how you will calculate the IL average? You know that this will be equals to I naught, and I naught will be equals to what? V naught by R, isn't it? So you can calculate the value of IL from here. So what will be the value of IL average? IL average will be equals to I naught, and that will be equals to what? That will be equals to dVs upon R. What is the D? 0.6 into 220 divided by R, which is 10 here. So how much will be the value of del IL? 13.2 ampere, isn't it? So you can calculate IL average from here. Now put the values here. this is 13.2, and del IL by 2, this will be 26.4 by 2. Again we will get 13.2, so the answer will be 26.4 ampere. I think the same answer you are getting. Yes, the answer is option B. So tell me, by remembering this fact, we can very easily solve this problem, isn't it, guys? Isn't it? Very good, very good. So now I am taking a 5-minute break. I will be right back after the 5 minutes. So stay tuned with the channel, and I am coming just after 5 minutes. Okay, so just take a break of 5 minutes, guys. everyone, welcome once again after the break. Am I audible and visible? Give me a reply. Am I audible, guys? Chat box. Very good. So, let me come to the next problem. Now, see this problem, guys. This belongs to the boost converter. Okay. Now, read the problem with me. The IGBT as shown in the figure is operating at a switching frequency of 20 kilohertz with a duty ratio of 40%. So, the frequency is 20 kilohertz and the duty ratio is 0.4. The peak to peak ripple in the source current and average current through IGBT are. So, what we have to calculate is, we have to calculate what will be the del IL, and we have to calculate what will be the average current through IGBT. IGBT is a switch, so we have to calculate the average value of current across the switch. These two things we have to calculate here. Okay. So, now see how do you approach for this problem. So, we don't remember what is the formula of del IL. Okay. So, what approach we have initially applied for buck converter, the same approach you will apply here for buck boost converter as well. So, guys, tell me, when the switch is on, so when the switch will be on, what will be the inductor voltage? The inductor voltage will be equals to what? It will be equals to Vs, isn't it? So, when the switch will be on, the inductor voltage is equals to Vs during the time the switch is on, or T on equals to dt. Now, this is equals to L dIL by dt. dIL is basically the del IL we are looking for, dt is the T on time or dt, and this is Vs by L. So, what will be the del IL, guys? Del IL will be Vs upon L into dt, or we can write dVs upon F into L. So, this will be the peak to peak current. So, see how easily we have derived this expression. We don't have to remember the formula. The same formula will be applicable if this would have been a buck boost converter. There are so many formulas that are very similar in buck boost and boost converter. Okay. Now, do we have all the data required for this? D value we are having, Vs we are having. What is D? D is given to us, which is 0.4. Vs is 220, I think. 200 it is. So, D value we have, D value is 0.4 and Vs value we have is 200 upon, what is F and L? L is 10 millihenry and F is given to us 20 kilohertz. So, 20 kilohertz and 10 millihenry. So, when you will solve it, can you tell me what is the value of del IL you will get? What will be the value of del IL, guys, that you will get here? Is it 0.4? Is it 0.4? Now, see whether 0.4 is an option. Yes, 0.4 is an option. So, option B is correct. So, this is an MSQ type of question, guys. So, one option we have calculated, peak to peak current. Now, we have to calculate the average switch currents. Are you getting the same answer? Whether you are getting the same del IL value, it is 0.4. Now, we have to calculate the average switch current. So, let us see how we will proceed for that. Average switch current. Okay. If we plot the IL waveform, and this is how you can calculate all the currents. If we plot IL waveform, the IL waveform is like this. Okay. This is our IL waveform. It is varying from I minimum to I maximum. This is the IL waveform that we have. This is dt time and this is 1 minus dt time, means this is T on and this is T off time. Okay. Now, guys, tell me one thing. This is what? This is the average inductor current here. Okay. And how do you calculate the average inductor current? If you see, it is the inductor current and the source current. Inductor will carry the same source current all the time, whether the switch is on or switch is off. So, what will happen? whatever current it carries all the time, that will be its average value. So IL average will be IS average. Okay. So average inductor current is basically the average source current. Okay. Now how do you calculate average source current? So guys, remember one fact, IS will be equals to I naught upon 1 minus D. How you can remember this thing? Whatever is the relationship between voltage and current, okay, sorry, whatever is the relationship between the voltages for a particular current, the same relation IS and I naught have. If you remember, the voltage across a boost converter is Vs upon 1 minus D. Similarly, you can write IS is equals to I naught upon 1 minus D. So this is how you can remember this thing very easily. If you want to really derive this expression, you can do one thing. You can do P input equals to P output if you are considering the losses to be negligible, and you will get this expression. Okay. So what is the IL average here? It is I naught upon 1 minus D. I hope this is clear to you. How you can approach for calculating the source current? Either you can use this trick, whatever is the relationship between V naught and Vs, the same relationship IS and I naught will enjoy. Or if you want to derive it, you can do one thing, P input equals to P output, considering no losses are there, and you will get this expression. Okay. But this is not we have to calculate, we have to calculate something else, and that is the switch current. Okay. So can you tell me, when do our switch carry current? The switch carry current when it is on and it is carrying the same inductor current, isn't it? The switch will carry the same inductor current during the on period. Similarly, if we talk about diode, the diode will carry the same inductor current during the off period. Yes or no? So we have to calculate here the switch current. So what will be the switch current? The switch is carrying the same inductor current during the off state. So whatever is on state, so whatever is the inductor current, we will plot it directly, whatever the shape it is having during its on state. Okay. So if you see, for dt time, the switch current is the same inductor current that it carries. If this would have been the diode current, so diode is carrying the same inductor current but for the off period. So we would have plotted this particular shape here. Now guys, if you see both this figure, you can see here the switch average value. The switch is carrying current for T on period. So from here you can directly write the switch average current will be D times the IL average current. And IL average current is what? The IS average current, and IS average current is I naught upon 1 minus D. So from here you can calculate the average switch current. It will be D into I naught upon 1 minus D. So put the values here. What is the value of D? D value is 0.4. And do we have calculated I naught? Do we have calculated I naught here? I think we haven't calculated I naught. So how do you calculate I naught, guys? See, V naught will be what? V naught will be Vs upon 1 minus D, and Vs is 200 upon 1 minus 0.4. So from here you can calculate V naught, and V naught will be 333.33 volt. Now for the load side, if you see, if this is our V naught, so the load side KVL will be what? The load side KVL will be V naught equals to E plus I naught R. So from here you can calculate I naught, which will be equals to V naught minus E by R, that is 333.33 minus 50 divided by 10. So from here you will get the value of I naught to be equals to 28.33. So that will be the I naught value. So this is how you can calculate the I naught here. Okay. So in order to calculate I naught, a little crisp was there, and that is, instead of having an R, RE is given to us. So this is a common sense, guys. If V naught is there, we will apply KVL and we will calculate I naught. Okay. Now coming back to this particular problem, put the value of I naught, which is 28.33, we have calculated, 1 minus 0.4. Now after this you will get the average switch current to be 18.9 ampere. Now do we have any options? Of course, option B is the correct option here, isn't it? Option B is the correct option here. Now guys, we have calculated the average switch current here. If suppose we would have been asked to calculate, average diode current, then what would have been the formula? If suppose diode average current would have been asked, the formula would have becomes 1 minus D times the IL average, okay? Because diode carries the current during the off period and it is the same current that the inductor is having, okay? So it is carrying a current for on period. So we have what we have done, IS average is equals to D times IL average. If diode would have been there, it would have been become 1 minus D times IL. So this is how we can calculate the switch current or diode current, okay? So this is a very interesting problem, very good problem, I have to say. Now after this, I'm having this problem, which is a very good problem as well. Now let me see, can you solve this problem as well? So what has been given to us, read this with me, a DC to DC boost converter. So again we have boost converter is shown in figure. If the duty ratio for the converter is 0.7, so what has been given to us, the duty ratio is how much? The duty ratio is 0.7, sorry, not 0.5. It is 0.5. Oh, again I am making the same mistake. It is 0.7, okay? So the duty ratio is 0.7 and the conduction time for switch. Now the conduction time for switch is given, means T on is given, and that is 285 microseconds, okay? Then the ratio of minimum to maximum current, guys, we have to calculate what will be the Imax upon Imin ratio. This is what we have to calculate, okay? Imax upon Imin ratio we have to calculate. So let's see what data we have and how can we calculate this problem. So if I talk about the Imax and Imin, you know both, whether it is Imax or Imin, you have to calculate it by applying this particular formula. IL average plus del IL by 2. This is what Imax. Similarly, what is Imin? Imin is IL average minus del IL by 2. So we require the value of IL average and we require the value of del IL here, okay? So what has been given to us? The duty ratio and T on time is given to us. So guys, from this you know that T on is what? T on is dt. So what will be T? It will be T on by D. Now T on is 285 microseconds divided by 0.7. So what will be the value of T? The T value will be 407.14 microseconds. So this is the T that we have obtained. So once we have obtained the T value, we can calculate the frequency. So what will be the frequency here? Frequency will be 1 by T. So it will be 1 divided by 407.14 microseconds. So you will get the frequency to be 2.45 kilohertz. So this will be the frequency, guys. So we have obtained the frequency. Now in order to calculate the del IL value, what we require? The del IL is dVs upon F into L. Now do we have the data for this? We have the value of D, we have the value of Vs, and F we have calculated, and the inductor is having a value 3 millihenry. So put the values of D. D is 0.7. What is the value of Vs? It is 180. Frequency is 2.45 kilohertz, and the value of L that we have is 3 millihenry. So from here you can calculate the value of del IL. So what will be the value of del IL? This will be 17.14 ampere. So you can calculate the value of del IL by 2, and that will be 8.57 ampere. So we have calculated the del IL value. Naru Gopal is saying 17.1. Very good. So we have calculated this much of thing. Now del IL by 2 we have. Now we require IL average. So guys, for IL average, tell me what is the value of IL average in a boost converter? It is equals to the same IS average we have seen in the previous problem. Okay. Now how do we calculate IS average? It is equals to I naught upon 1 minus D. Whenever you have to calculate the source current, just remember what formula that particular converter has for output voltage. The output voltage formula is V naught equals to Vs upon 1 minus D. So same formula you will apply for IS. IS will be I naught upon 1 minus D. This is how you can remember this. Okay. Now what will be the I naught value? In order to calculate I naught value, you will put again V naught by R. So this will be like this. Now for V naught, you will again put Vs upon 1 minus D. So this will be 1 minus D square by R. Now we have all the data. So it is 180 divided by 1 minus 0.7 square into what is the value of R? It is 10 here. So from here you can calculate the average inductor current, and the average inductor current will be 200 amperes. So this is how we will get the value of IL average and the value of del IL by 2. Now what will be the Imax? So Imax, it is IL average plus del IL by 2. So what is IL average? It is 200 plus del IL by 2 is how much? 8.57. So this will be 208.57 ampere. Now what will be Imin? Imin will be IL average minus del IL by 2. So 200 minus 8.57. So you will get how much? 191.43 ampere. What we have to calculate is the ratio of Imax to Imin. So Imax is how much? It is 208.57 and Imin is 191.43. So what will be the ratio, guys? This ratio will be approximately 1.089, or we can say 1.1. So do we have the answer? Yes, of course we have. Option A is the correct option here. Naru Gopal is saying I average will be 200. How? Naru, calculate this by this particular formula. Apply this formula. Are you not getting the same answer? Are you not getting the same answer here? Apply this formula and you will get the same answer. Are you getting the same answer? 180 upon 0.3 square into 90. Yes, okay. Now you are getting, okay. So are you enjoying this fact that we are not remembering any formula? Whatever formula is required, we are calculating that there only, okay. So no pressure you have to take on your mind for remembering so many formulas. Just focus on other subject for that part. You don't have to take care for remembering the formulas of power electronics. You can derive those formulas anywhere and any point of time you want, okay. Now coming to this particular problem, this is a very good problem. These type of problem have been asked so many times in the GATE exam, and I am sure this will be asked once again, okay. Now read the problem with me, guys. A boost converter is feeding a variable resistive load as shown in the figure. So again we have a boost converter. If the switching frequency is 100 kilohertz, so whatever is the data given, just write it. Switching frequency is how much? 100 kilohertz, okay. And the duty ratio is 0.6. So D is given to us. What is D? D is given to us, it is 0.6. It gives an output voltage of 48 volt. Output voltage is 48 volt from a 12 volt supply. Vs is 12 volt. The value of R in ohm, that will make the inductor current just discontinuous, means we are operating at the boundary of continuous and discontinuous conduction. So guys, tell me the fact, whenever you see that particular line in a question, what you have to do? Can you just answer me? Whenever you see that particular line, what condition we are applying here? Whenever it is given that a boundary of continuous discontinuous conduction is there, what we are doing? Can you just tell me what we are doing whenever this such kind of scenario we are seeing? Whenever it is given to you that the converter is operating at the boundary of continuous and discontinuous conduction, what we are doing is that we are applying I minimum to be equal to 0. What is I minimum? I minimum is IL average minus del IL by 2. Okay, this is equals to 0. Now IL average here is I naught upon 1 minus D, minus it is dVs upon FL. Okay, so finally when you will put the value of I naught as well and solve it, what value of L you will get? You will get the value of L to be D 1 minus D square R by 2F. Okay, so that will be the value of inductance. Okay, in case of, very good Naru, in case of buck converter, we have this formula where L is equals to 1 minus D R by 2F. Okay, in case of boost converter we have this formula. Now what students normally does, they used to remember this formula. I don't think so that guys that you don't have to remember the formula. You can derive this anywhere, anytime you want. We don't have to calculate L, we have to calculate the value of R. So the value of R will be L into 2F divided by D 1 minus D square. So put the values. L is 100 microhenry. What is value of F? F is having a value 100 kilohertz divided by D. What is D? 0.6, 1 minus 0.6 square. So you will get 208.3 as answer. 208.3 ohm, that will be the answer. Naru, you are again have solved the questions correctly. The same answer I am getting too. Well done, very well done. So Nikhil, Subodh, Sachin, Rupesh, Saurabh, are you getting the same answer as well? Very well done. Okay, so again, how to approach for this formula, is that clear? Do not waste your time in remembering these formulas. Okay, let me move to the next problem. Now see this particular problem. This is also a very good problem. This is also a very good problem. See what has been given to us. Now the first time we are moving towards the buck boost converter. So in the figure shown below, this is a buck boost converter. The switch is operated at a frequency of 30 kilohertz. Write these facts. The frequency is 30 kilohertz. With a duty ratio of 0.55, D is given to us. It is 0.55. If the power absorbed by the load, that is P naught, is 3200 watts, then average value of inductor current will be. What you have to do is to calculate the average inductor current. So you have to calculate average inductor current here, guys. So let me tell you that average inductor current, whether it is a boost converter or whether it is a buck boost converter, it remains the same. Okay, you know how we have calculated the average inductor current in case of boost converter. So average inductor current in case of buck boost converter is the same, having the same formula as we have in case of boost converter. Now we have the required formula, and that is IL average IL average is I naught upon 1 minus D. So D value we are having, but do we have the value of I naught? No, we don't have. So we have to calculate the value of what? The value of I naught. We have to calculate the value of I naught. So how do we calculate the value of I naught? See, the power is given to us. Power is V naught into I naught. Power is given 3200 watts. And what will be the V naught? V naught is also not given. So it is a buck boost converter. So in case of buck boost converter, you know, V naught is D upon 1 minus D times Vs into I naught. Okay. So from here we can calculate the value of I naught, which will be equals to 3200 1 minus D upon D Vs. Now everything we have 3200 into 1 minus the value of D is 0.55 and the value of Vs we have is 100 volt. So from here guys, you can calculate the value of I naught, and that will be 26.18 ampere. Okay. Now come here and put the value 26.18 upon 1 minus 0.55 and you will get the value of IL average, and that is 58.18 amperes. Are you getting the same answer guys? Tell me, are you getting the same answer? What has been asked? IL average. So remember just one fact, IL average is same in both the case buck boost converter and buck boost converter. And what is it? It is I naught upon 1 minus D. Okay. What is it in case of the buck converter? In case of buck converter, IL average is equals to I naught. Okay. So we have done variety of problems. We have calculated everything from where we can expect a gate question, isn't it? Now let me move to the next problem. Now see, a very good problem guys. We have solved all the problem which belongs to the continuous conduction, or the converter is operating at the boundary of continuous and discontinuous conduction. This is the first problem that we have, which is related to the discontinuous conduction. Okay. So what has been asked in this question is, in a buck boost converter, the current waveform through the inductor is shown below. The correct relation between input and output voltage will be. Okay. So what will be the correct relation between input and output voltage is what we have to determine. Ultimately we have to determine what is the output voltage in terms of input voltage. Okay. So this looks to be a very different problem, very tough problem, but it isn't so. How we will approach for this? Guys, if we don't have anything, if we don't remember anything, just draw the figure of that particular converter. So when it comes to the buck boost converter, so what is the figure of buck boost converter? The circuit diagram of buck boost converter. We have the source voltage, and after that what do we have? See here, this was the buck boost converter problem that we have done, isn't it? So you can copy this particular figure here. So we have this switch, and then what do we have? See here, we have after the switch we have inductor connected in parallel. Okay. And after the inductor we have this diode connected in this manner, then we have a capacitor, and then we finally have the resistor. Okay. This is the voltage that we have here. This is the inductor voltage. This is the inductor current, the diode, the switch that we have, and the value of that and the Vs that we have. Now see from here guys, if I ask you what will be the, when the switch is on, when suppose the switch is on, at that time when you will apply the KVL, what will be the VL voltage? At the when the switch is on, Vs is equals to VL. The inductor voltage is exactly equals to Vs. When the switch is off, so when the switch is off, you have to apply KVL in this particular circuit. Okay. So in this particular circuit, when you will apply KVL, you will get VL equals to minus of V naught, isn't it? This is what you are getting. Now see, we have a current waveform given to us. We have a current waveform given to us, and what is that current waveform? See the current waveform, and from there we can derive rest of the things. This kind of current waveform is given to us. Okay, where this is T, this is 0.8t, and this is 0.3t. Okay, this is the waveform of inductor current which is given to us. Now, can you tell me one fact? Can you just tell me one fact? At the moment when the inductor current is increasing, that is the moment when the switch is on. At that time, what is your inductor voltage? At the moment when the inductor current is increasing, at that time your inductor will be storing the energy, and that is the moment generally in the converter when the switch is on. So when the switch is on, the inductor voltage is how much? The inductor voltage is how much? It is equals to what? Vs. Okay, so you have Vs here. Okay, you have Vs here. And now from this particular moment, what is this duration? This duration is normally how much? 0.3 t. And during this moment from 0.3 t to 0.8 t, you can see the inductor current is decreasing. So when the inductor current will decrease, whenever you will switch off, whenever your switch is off, at that moment, that is the moment your inductor current will decrease. Inductor will release its energy. So at that moment, can you tell me what is the inverter voltage that you are having? What is the what is the inductor voltage that you have at that moment? So at that moment, we have an inductor voltage which is equals to how much? It is equals to minus of V naught. Okay. And rest of the moment you can see we are having discontinuous mode of operation. So no voltage will be there. Okay. So this kind of waveform we will get. So what is this instant? This is 0.3 t. What is this instant? This is 0.8 t, and this is t. Okay. Now you know that whatever will be the condition in these converters, VL average will be equal to 0, isn't it? VL average equals to 0 means the volt time balance. Okay. So what if you apply the volt time balance, what you will get? Vs into this particular duration. How much is this particular duration? 0.3 t. Okay. This is equals to this area. How much will be this area? This area will be V naught. And what about this duration? How much will be this duration, guys? How much will be this duration? Okay, tell me, this duration will be how much? This duration will be 0.5 t, isn't it? So what you will do, you will apply, you will write 0.5 t here. So from here, can you tell me what will be Vs? V naught, it will be Vs 3 by 5 of Vs, isn't it? See, this seems to be a very difficult problem. This seems to be a very tough problem. It has an appearance like that, but it isn't so, guys. The fundamental principle that you have, suppose somebody haven't gone through these converters, even then he can apply this particular things and he can solve this question, isn't it? Tell me, guys. So Nikhil, are you getting the same answer as well? So what you will get, let me see whether we have this option as well. 3 by 5 of Vs, yes, we have this option. Okay, option number D will be the correct option. So see, by simply approaching the fundamental concept, okay, forget about different multiple formulas, multiple lots of tricks, guys. Simple fundamental you have to remember, and not only you will score good in GATE, you can be a topper as well. Okay, so believe upon yourself. Believe that you are the legend in your own legacy. All you have to do is to put your efforts into it. Okay, sir, your solution method is too simple. Thank you, Naru. Thank you. Very good. Okay, so look into these, understand very easily. Thank you so much. So revise this problem as much as you can, guys, and believe me, these 4 marks of this particular chapter, nobody can take those marks from you. Okay, that's my promise with you, and I am pretty intent to keep my promise. Okay, chalo, let me take you to the next problem. See, this is a very good problem, guys. Thank you Gopal, thank you Naru, thank you Nikhil. So now see this particular, this is also one of the good problem. Okay, and this type of problem has never been asked in GATE. So you can expect this problem in upcoming GATE exam. Okay, so just read this problem with me. A DC to DC converter is used in regeneration braking mode of a DC series motor. So motor is being used in regenerative mode, means instead of motor it is acting like a generator, means it will be delivering current to the converter, not taking power from the converter, it will be delivering power to the converter. Okay, it is operating on a duty cycle of 65%. So first of all, whatever data has been given, put a habit of writing that. Okay, so duty cycle is given to us and that is 0.65. The average value of armature current is 110 ampere, guys. That will be the load current, that will be the output current, isn't it? If suppose this converter is delivering power to the motor, then in that case this would have been your I naught. So what happens if the motor is delivering power to the converter, it is operating in the regenerative mode, this in that case also this is your output current. Okay, now it is continuous and ripple free. Very good. The power feedback to the supply, whatever power is flowing from here to here, that power you have to calculate, and this power calculation is very simple. This power will be V naught into I naught. What will be the V naught? V naught will be the terminal voltage of this motor. So let this be the terminal voltage of the motor and let it be V naught, isn't it? So you have to determine first of all what will be the V naught, because I naught is given to you. So guys, tell me, since the motor is driving this converter, so what happens? First you will turn on the switch and then you will turn off the switch. This is how we will proceed to the any of the converter, whether it is buck boost or buck boost. So first when you will turn on the switch, what will happen? So when you will turn on the switch, guys, tell me when the switch will be on. So when the switch will be on, this is the direct shunt. So what will be the output voltage? The output voltage will be 0, isn't it? And what will happen when the switch is off? So when your switch turns off, this output voltage immediately will be equal to what? Vs. Because when the switch will be on, the inductor polarity will be like this, isn't it? And the inductor will be storing the energy. Yes or no? So this will be the inductor polarity at the beginning, and at the end the inductor will be releasing the energy and its polarity will be like that at the end. Yes or no? So due to that polarity of inductor, diode will get on. So when the switch will be off, inductor will release its energy, it will turn the diode on and output voltage will be equals to Vs. So when the switch is off, guys, what do we have? At that time the V naught is equals to Vs. Now tell me the fact, Saurabh, Gaurav, Gopal, Nikhil, Naru, are you able to understand these two concepts? When the switch is on, the output voltage is 0, but when the switch is off, inductor will be releasing the energy, it will make the diode on and your output voltage will be exactly equal to the Vs. Yes or no? Naru has calculated the answer as well. Very well. Are you getting this fact, guys? So whatever we have obtained here, let me plot that first. So what we have obtained during the on period, okay? During the on period, let this be the on period. So during the on period, what is the output voltage that you have obtained? During the on period, the output voltage is 0. But during the off period, what is your output voltage? So during the off period, the output voltage is equals to Vs, isn't it? The output voltage is equals to Vs. So if I ask you what will be the average output voltage, what will be the average output voltage? So anybody, by looking into these waveform and the experience that you have gained by solving all these problems, you can instantly comment that V naught average will be 1 minus D times Vs, isn't it? And D is given to you, it is 0.65. Vs is also given to you, it is how much? It is 580. Okay. So from here you can calculate, very good Naru, very good. From here you can calculate the average output voltage. And what will be the average output voltage? It will be 203 volt. Now, when it comes to the power delivered by the motor to the source, that will be equals to the average output voltage into current. So you have calculated this 203 and it is 110. So how much answer you will get? You will get 22.33 kilowatt as an answer. Let me see whether this is an option or not. Yes, we have option B, which is exactly the same. And Naru has already calculated that. Very good, Naru. Well done. You are in a great touch of the subject. So this is how we will approach towards this problem. Okay, last two problems were really very fantastic problem, guys. Focus on that, practice them as much as you can, and you will get a same problem there in the GATE exam as well. Okay, yeah. Now coming to this problem. Now I have seen from the past GATE papers that now GATE authority is asking questions from interleaved converter as well. Okay, what they are, because what happens normally, we connect two or more than two converters in parallel, we interleave them. Okay, what is the purpose of doing that? If you connect so many converters in parallel, ultimately what will happen, guys? Ultimately what will happen? You will reduce the ripple current. Okay, you will reduce the ripple voltage. So the capacitor requirement, okay, whenever you have, if suppose you have studied any of the converter, so in the assumptions there is one common assumption that we will keep the capacitor value very high so that the output voltage ripples will be neglected or will be reduced. So in order to get that capacitor value to be lowered, what we do, we connect so many, we will do this particular parallel combination of these converters like this. So what happens, this is done to reduce the del IL or del VL content. Okay, by doing this we can reduce del IL, del V naught, and ultimately we can reduce the cost of, ultimately we can reduce the value of C as well. Okay, we can reduce the value of C as. So that is the purpose of doing this particular thing. When we are connecting so many converters in parallel, what will happen when we are connecting so many converters in parallel, guys? So what will happen? Let me just read the options. The switches are operated 180 degree out of phase. Okay, this phase shift is determined by this particular fact. The phase shift is 360 divided by n, where n is the number of converters used. So tell me, how many converters we have used? We have used two converters here. So what will be the phase shift here? The phase shift will be 180 degree. Okay, so this is how you will calculate the phase shift. Suppose we have used 4 converters in parallel, the phase shift would have been 90 degree. Are you getting this fact? Naru, Nikhil, Gopal, Saurabh, are you getting this fact? Sachin, are you getting this fact? Rupesh, the phase shift will be 360 by n. Okay, n is the number of converters we are interleaving. Okay, so here we are using 2 converters, so phase shift will be 180. If suppose we have used 4, it will be 90 degree. So can we have the second option correct? Because A is the correct answer here. The second answer says the switches are operated in phase with each other. So that cannot be a correct answer, isn't it? We never operate these converters in phase. Okay, they are always operated in out of phase with each other. Third option is inductor current are 180 degree out of phase with respect to each other. Exactly correct. Okay, inductor currents IL1 and IL2, they are exactly 180 degree out of phase with each other. Guys, what happens? See, at a time we will be having one converter operating and second will be off at that time. Okay, means one switch will be operating at a time and other will be off. So when first switch will be on, what will happen? If suppose first switch is on, inductor current is increasing, and second switch is off, so inductor current will be decreasing. Then again we will turn off the first switch, it will be decreasing. Again we will turn off the second switch, it will be increasing. So this is the pattern of IL1 and this is the pattern of IL2. Okay. So what will happen? Ultimately what will happen, guys, the net current, the net inductor current will have this particular pattern. The net inductor current will have this particular pattern, which is IL1 plus IL2. So here whatever is the ripple, if that ripple is del IL, then ripple here is del IL dash. So what we have by doing this, we can have less ripple as compared to the first one. Okay. So this is high. I haven't attempted this type of question, sir, but you have made it available. Very good. Thank you so much, Naru. So see, if switch 1 is on, its inductor current will be increasing. At the same time, switch 2 will be off because we are operating them at 180-degree phase shift. So you can see if inductor current 1 is increasing, at the same time inductor current 2 is decreasing. When inductor current 1 is decreasing, at the same time inductor current 2 is increasing, because we are turning one switch at a time and operating them at 180-degree phase shift with each other. So ultimately what will happen, if the ripple current here is del IL, then the combination will have less ripple current, and this is the purpose of doing this interleaving. Okay, this is the purpose of connecting these converters in parallel. So inductors currents are 180-degree out of phase with respect to each other. Isn't it correct? Yes, of course this is correct. Inductor current will be 180-degree out of phase with each other. If we have used 4 such converter, inductor current would have been 90-degree phase shifted with each other. If we have used 6 converter, inductor currents will be 60-degree phase shifted with each other. So this kind of phase shift we will get depending upon the number of converters we are connected in parallel. Okay, so option C will be correct. Now D, each inductor supplies one of the load current and output current. Guys, now can you tell me the inductor current here? Each inductor supplies one half of the load current and output current. So inductor current here is IL1 plus IL2. So if you are using identical inverter, of course IL1 and IL2 both will be half of the IL, isn't it? So this option will also be the correct option, isn't it? If suppose we have used 4 converter, instead of 1/2, this should be 1/4. So option number A, C and D, all the options are correct. Okay. So guys, this type of question you can expect in this year's GATE exam. Is that clear to you guys? Tell me, is that clear to you all? Is that clear to you all? So this is the last question that I have, and the last 3 questions that I have discussed as superb question. You can expect any of them coming in this particular GATE exam. Okay. Yeah. Now after that, so this is all about option D. एक बार explain कर दूं. See, Naru, what will happen? Your IS current divide here, and it will become IL1 and IL2, isn't it? So what will happen? What is IL1? IL1 and IL2 both are equal here, and they will be IS by 2. Okay. If suppose we have used 4 converter, this should have been IS by 4, isn't it? If suppose we have used 6 converter, this would have been what? This would have been IS by 6. Okay. So your source current is equally dividing among the converter. That is what has been asked in option D. Okay. Is that clear? Yeah. So now this is all about this particular chapter, guys. We have solved so many interesting questions, and I have made this very, very clear to you how you can approach towards the particular formula required to solve any of the problem. You don't have to take any of the load in order to remember so many formula. This subject is very, very simple, guys. As far as the concepts are concerned, if you have cleared your concept, you just remember the circuit diagram, you can derive any of the formula required in order to solve a question, isn't it? So pay attention on other subject as well. Do not bother more about power electronics. So today we have discussed the power semiconductor devices, and we have discussed the DC to DC converter as well. So if you have really enjoyed this class, and if you have really enjoyed the questions and the solution as well, you can have the better experience if you join us. Okay, so guys, for that, visit our website, which is www.imsindia.com, and there if you go into the GATE ME section, you will get all the features that we are offering. So we are basically offering 4 types of program. One is the classroom program, fully offline mode; hybrid classroom program, where 2/3 online and 1/3 offline content will be delivered to you. Okay, and we have exclusively live online program. So if you can't visit to any of the center, you can join us in this manner, which is running completely in online manner. And guys, if suppose you are a working person or you don't have any time, we enjoyed a lot in this session, sir. Thank you so much, Gopal. So if you think that you don't really have time, you can join our self-learning program as well, where we will give you the content, the recorded content. You can go through that and you can enjoy your preparation. Now, what all these about? So if you are joining classroom program, you will get a 750 plus hours of offline classroom session. This will be 100% offline, and you will get 22 to 30 books. This include theory books of each and every subject and exercise book of each and every subject. In theory book, you will get one of the best content, okay, one of the best content that can be available for a particular subject, and it is full of tricks, it is full of the concepts. And in our exercise book, we have 4,000 plus practice questions. So if suppose you have practiced that much amount of question, nobody can stop you by becoming a topper in the GATE exam. GQB, we offer GQB as well, that has the past GATE questions. We have a dedicated doubt solving portal. Suppose you have any doubt, you don't have to wait for, immediately take a snap of this, and we have a dedicated doubt portal. Post your problem there and it will be solved within 24 hours. This is something that we are doing, nobody else is offering. Okay, my plan strategy session, here you can discuss all your problem related queries, how to study a particular subject, how to revise a study, how to revise a particular subject, how can we approach for a particular subject, and what to do and what not to in order to be well prepared for the GATE exam. So this is a kind of one-to-one interaction that you can have with us. Okay, and we have a very good test series that includes 130 plus tests, and that has chapter test 84 plus, sorry, that has chapter test 84 plus chapter test we are offering, subject test basic plus advanced level, multiple subject test, and of course the AIMTS test series, the mock test series that we are offering. Apart from that, you can have the post GATE interview guidance as well if you join this particular program. After the classroom program, we have hybrid classroom program as well. It also include all these features that we are offering in fully offline mode, but the only difference is that 2/3 of the content you will get in online offline case, and 1/3 content will be offered to you in online manner. Okay, now exclusively live online program. It also have every feature that I have discussed for the last 2 program, but the only difference is all the content, the number of hours of the classes that we were delivering there, we will deliver this content to you in an online manner. Okay, so guys, it is very difficult to manage. If you are working somewhere or if you are a college student, it's very difficult to manage your preparation along with the college. So if you are really worrying for that particular thing, we are the solution, because we are providing this particular live online program where we are offering you classes right after your college. So you can very well manage your college and your preparation both at the time. Then we have self-learning program, where you will be given a 400 hours of video lecture in a recorded manner, and all the features you will have apart from the AIMTS test series. You will enjoy all the features here as well. Okay, so this will be in a self-learning program where you will be given a content and you have to explore it by your own. Okay. Now, we believe in LPT methodology. First, you have to learn something, and after that, you have to practice, and after that, you have to test yourself. So, first, we will give you the kind of content, the kind of motivation that you require, and then we are offering you the enough amount of practice material as well, enough amount of test series as well, where you can test yourself. So, we are following the LPT methodology that is best suited in order to become a topper in any of the exam. Okay. Now, see our test series. We have 84 plus chapter test. We have 12 subject test. We have subject wise advanced level test. This is basic level test, and this is advanced level test that we are offering subject wise, and then we have combined few subject, and that is called multi subject test, and after that we have 12 mock test series as well. So guys, we are offering enough amount of material as far as our test series is concerned, and our test series is among one of the best. Okay. Now, after this, if you want to join us, you can test us before you actually join us. So visit our website and go to this GATE ME corner, and there you will see there is a zero fee program tab there, where you can enroll yourself and you will get 100 plus hours of free videos, 12 chapter test, 6 subject test, and 6 past GATE papers. So join this and then decide how much efforts we are putting. You can test us and then you can join us. So this is something that we are offering, guys, where you can join us in a free manner without paying without paying anything. You can join us and you can check these things, and then you can take a decision to join us full time. Okay. Yeah. Now, this is the student portal. Doubt how the appearance of the student portal is like this. You can see here. So there is a dedicated doubt portal here as well. So this is our doubt portal. Whenever you are studying, whenever you are covering some content, definitely you will be having doubts. So we have a dedicated doubt portal where you can post your doubt, and it will be solved immediately in 24 hours. So this is something which is very, very useful for students. Okay. Now, one-to-one mentoring session and one-to-many mentoring session. While you are preparing for any of the exam, you will get n number of doubts. Now, you need some teachers, you need some motivators who can solve your doubts instantly. So for that, we have this particular initiative, which is unmatchable, uncomparable. You can come to us, you can join in an online manner. You can have one-to-one mentoring. We are offering you one-to-one mentoring session where you can discuss all your doubts related to the preparation, related to the revision, related to the exam pattern, and related to everything you want. Okay. So this is a kind of thing that is unmatchable, guys. So this is the end of today's session. I hope you all have enjoyed this session, where we have discussed so many important questions, so many important concepts, and so many important tricks, and last but not the least, how you can approach for the particular formulas required to solve a question of power electronics. So these sessions will be very, very helpful for you, because we have designed questions like that, guys. In the upcoming GATE exam, you can definitely have a question from this particular series or the concept that we have discussed. So this is going to be very, very helpful for you. So today I have discussed power semiconductor devices and DC to DC converters. Don't forget to be there from 6 p.m. to 9 p.m. tomorrow as well, because tomorrow we will also have a session on power electronics where we are going to discuss about the rectifiers and inverter. Okay. When it comes to power electronics and specifically the chapters like rectifiers and inverters, the biggest nightmare of students are how to remember the different Fourier series of each and every converter. So if you don't want to remember so many things and if you really want to enjoy, and if you want to have the tricks to solve these particular problems related to the Fourier series expression, come with me tomorrow from 6 p.m. to 9 p.m. and I will disclose the tricks how you can remember those Fourier series expression very easily, and you can solve all the questions. Okay, so if you have joined today's session, if you will join tomorrow's session, I am very sure that you are going to score as many as you can in power electronics. So this is the end of today's section. Thanks for being such a patient audience, guys. Thank you so much for joining. Thank you.